Kind of the organisers to invite me. I'm going to repay their kindness by lowering the tone of the meeting very considerably and talking about some slightly old work that I did. I began in an industrial lab in HP Labs some years ago for very practical reasons to do with understanding the relationship between investments in information security technologies in the context of large-scale systems. So we were developing some modelling technologies to help us understand the costs, the benefits and costs of what we were doing. However, I realised recently that there were some interesting logical properties that might be coming out of this stuff now, so I've revisited this work a little bit recently, and I thought that there might be some small interest to this meeting in some of what's going on. So what I'm going to do, I'll just start out by taking...
It's very hard to hear.
I'm sorry, is the mic not working?
It doesn't seem like it to me.
It sounds to me like it is from the echo, but yeah. Okay.
Barely hear you. Yeah.
Okay. 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 Try that. Is that better? Okay. So I'll try shouting. What I'll just do is review some of the background mathematical setup that we used. It's not all that complicated, but it's surprisingly delicate in places. So what we started by doing was just taking seriously what are the kind of core notions of distributed systems. So you go and get a big book on distributed systems, you read it and you kind of reflect on it. And so we identified the idea of location, which is the basic underlying structure of a system, the places where stuff happens, the connectivity between those places, the idea of resources, stuff that lives at locations, and the idea of processes that deliver the services that the system is providing by manipulating the resources that live at locations and stuff like that. When you build a model of a system like this, you have to remember that it sits inside an environment. But of course, you're not going to model the environment because the environment is kind of everything else. So you just want to model that in terms of the events that the environment causes to be incident upon the model that you care about. Okay. Now the business was about understanding big, complex systems, probably at a quite crude level of detail, but we nevertheless needed to think about how these things compose together. Mathematically, we wanted to employ the minimal structures that would do the job for us because we were interested in really quite practical things, and everything I'm going to describe today, or almost everything I'm going to describe today, is implemented and was deployed in real systems work in Hewlett-Packard. Some of it was even sold to customers for actual money. And just to remind you, we were concerned with practical modelling of the relationship between security policies and investments in security technologies and the way in which systems were constructed and used. So locations, we were working with topological structures of one kind or another, but mostly just with directed graphs because they were simple and would do the job. The resources that we were working with can be seen as arising from the logic BI's resource semantics, which is the logic and its semantics that give rise to separation logic, which has recently had a great deal of success in program verification. The process component was basically a version of SCCS. It's known as SCCS from 1983, with just a little bit of refinement to talk about how processes and resources interact. In particular, I think Mike did something a little bit like this many years ago. But in particular, I won't tell you about this in detail, but there's an operator which generalizes restriction in a particular way to talk about how, yeah, now you recognize it. Yeah. Okay. And so, and environment is just represented stochastically. I'm not going to talk about that at all today. Okay, so just to tell you what's going on very quickly, we're talking about locations, resources, and processes co-evolving via actions to a new location, a new resource, and a new process. These are driven by, in practical models, driven by a signature of these things called modification functions, which tell you what a particular action does to a particular resource. I'm actually suppressing location from here onwards because it just takes up too much space to talk about it. So you'd also have locations here, and you'd also get a pair of resource and location here, but just suppress that. You can code everything in location anyway, in resource anyway, if you really want to. Of course, you can code everything in process if you really want to, but then you pay a massive conceptual and computational price that you didn't want to pay. So, but just for presentational purpose, let's just work with this signature, which tells you what actions do. And I'm going to just highlight a couple of key things. I mean, This is a synchronous calculus, so we can work with how a resource and a process evolving here and another resource and a process evolving here get combined using concurrent synchronous product and a tensor product on resources to give you the new thing. Similarly, we've got a choice operator going on, and we do actually need this other combinator plus here for a technical reason. So this is where this semantics departs from the semantics of separation logic, in that we have these two combinatorial operations that have to have a lot of laws relating how they behave, distribution laws and so on. It's actually much closer to concurrent separation logic than separation logic, although even so, the semantics is a little bit different. Okay, that's all I'm going to say for now there. Of course, in the sense of Hennessy and Milner and Van Penton, these systems always come with logics, and this one looks a bit like this. So here we can start with just with classical propositional logic. You can make this intuitionistic if you prefer, but everything gets a little bit more complicated. Then we can add some action modalities, and so far we've got Hennessy-Milner logic. We can then add star and magic wand, and then we've basically got separation logic at this point, up to a small amount of coding. And then we can get all sorts of exotic modalities. These are more multiplicative modalities. We can also have multiplicative quantifiers in addition to additive quantifiers. I'm not going to tell you about any of that because I don't have time. But the only thing to note here is that this is kind of the simplest. The thing I'm talking about here is the kind of this is awkward. I'm sorry. The simplest possible multiplicative modality just talks about the possibility of an action with respect to additional resource. Now, there's a whole logical theory of how to set this up and have lots of choices here with specific additional resources and so on. But that's just an example of the kind of thing you can do in this space. Again, here you have the decomposition via star, and there are some separation conditions that I haven't bothered to write here, and many of you all know what they are anyway, or can imagine what they might be. Okay, but this is the key thing. This is a key thing from the point. This is as far as the early days of this work went. This was the key way in which we kept control over the decomposition of complex systems. Okay, just a few remarks on the left theory. You have the idea of logical equivalence of processes, just in case they satisfy the same things always. Bisimulation is trisimulation, and the standard complete result is the Hennessy-Milner Van Bentham equivalence. And in this case, this is really not as simple as you might think. If you try to do this using the basic resource semantics that you find in BI and separation logic, it does not work. You only get completeness for fragments of the logic that don't include a few multiplicative things. You can have star, but you can't have magic wand, you can't have the modalities. However, if you have the combinatorial structure of plus and times that I introduced to begin with, then you can track stuff appropriately and get the completeness theorem. There doesn't appear to be any expressive price in moving to the different resource semantics, but it does lead to a slightly different style of modeling than you would have. Okay, so just a few remarks to this. I just made that remark. If you really want to see the theory of this, there are a bunch of papers in journals like MSCS and TCS and GLC and stuff where all this has been worked through in boring detail. But the main point is that you do need this combinatorial structure to track the choice operator and the concurrent product as they evolve. Okay, that's enough maths. Now, what about building of models? So the kind of modeling we were doing here was good old-fashioned mathematical modeling in the sense that engineers do it. Right, so this is not specification verification from the ground up. It was you've got a big complex thing, you observe something about it, you build some models, you work out what the models tell you, you check those back in the real world, and you refine the model until you're happy with it. This is what engineers do. Now, everything I've said so far is completely scale-free. I mean, in fact, some people are applying the kind of stuff I've been talking about to weak memory at the moment, so it goes right down to the bottom. But this is the way in which this stuff is used. It's a relatively subtle distinction, but it is important. The reason separation logic works so well, by the way, is that you can build engineering models of memory and its dynamics in this style, but that happens to correspond in a very strong way to a piece of logical modeling that captures the scalability in exactly the right way. That's why separation logic works. Right? These two things come together. Okay, so we did a lot of this. We really did do a lot of this work in Hewlett-Packard. We did actually get money for it, and just recently it's come up again as a tool that may be useful in lots of industry-based projects that are coming into the Turing Institute. Okay, so yep, this is essentially scale-free. This is just an aside. Things to remember when you're building models.
David, what do you mean by scale-free?
When I write an action, I don't care whether it's a great big complex thing or a really tiny thing. As a modeler, you can just choose to call something complex a single anatomic action or not, and everything will match that. You're not making any commitment to particular granularity. Okay. Because of that, you need to choose your abstraction level very carefully to fit the problem that you're trying to solve, so you can answer the questions you want to answer. So it's no good talking about packet level network traffic if you actually want to talk about the costs and benefits of a particular IDS device and how many of them to scatter around the network. It's just the wrong level of abstraction. So. Okay. In terms of implementation, most of this work was explored predictions of the consequences of policies for systems using Monte Carlo style simulations. There are more model checking tools available, though they are a bit restricted and not very well developed. And remember, when you build models, the reason to build models is that you want something simpler than the thing you started out with, but that has consequences. Also, when you're building models, sometimes it's better to have a really crap model next week than a really beautiful model in 6 months' time. The problem may have gone away in 6 months' time. Okay, so here's an example of the kind of thing we might do. This is a very simplified example to fit it onto a slide and to be able to talk about it. But here are 3 models. The big one in the middle is a model of access control into a building. So the idea is that you come in from the outside, you enter a lobby, and there's an entryway which is perhaps card access controlled. And if you enter and you've forgotten your badge, you have to go to reception to get a replacement. And once you've got it, you can go back and go through into the inner office. And there are all sorts of bad security things that can go on here. People can tailgate you. People can steal your card, and so on. Or you can get bored and decide not to queue for a badge, so tailgate somebody else. All sorts of bad behavior can go on here. So what sorts of questions do you want to answer about this model? You want to answer about what is the right number of access gateways? What is the right number of reception staff? What is the right number of timing? What is the right timing for various things that are going on? How many guards do you need to keep an eye on what's going on? All these questions are things security officers care about. So, and they're quite easily answered by simulation, actually.
So is the model a model of the static connections in the system, or is it a model of the behavior? Because up there you have behavioral stuff, and down there you have...
It's basically behavior. You've got a bunch of locations, and at the locations live some resources, and what we do is you fire an agent at it and see what happens as the agent interacts with the resources that are available. You kick all this stuff off by stochastically firing an action at the edge of the model and see what happens. Does that make sense? Yeah. So there's another model here, which is the place you get... Oh, sorry. The place you get to once you get through the reception area, you get into the office where you can do all sorts of stuff like print files and leave USB sticks lying around for people to steal and things like that. And then on the other side, there's how you get there in the first place, where you start at home, you take public transport, you take your car. Eventually, you leave your laptop on the train, all that kind of stuff happens, and eventually you get to the office. Okay. So. These 2 people are smiling when I talked about leaving laptops on trains because they know what I do.
Related to what Rana just asked, you mentioned the idea of security guards and people like that. Yeah. So you're actually taking people into account as well as the computational... Absolutely. So people are modeled as processors, basically. Yeah. You can also model them as resources, and which you choose depends on exactly what you want to do. Okay. So in fact, in this particular model, people are modeled as both different sorts of people are modeled both as processors and resources. So the agents who are doing the attack, who are doing the penetration of the model, either legitimately or illegitimately, are modeled as processors. But the number of guards is just a resource count, for example. Most of the resources you use end up getting modeled as natural numbers, modeled as natural numbers, but not always. Computer memory is the obvious.
Okay, so what we're really going to talk about now are these little yellow boxes. These two things here, the interfaces between the models. Now, an interface what's going to happen is that there has to be a shared location that is identified as part of the interface. There has to be a bit of stuff here, and I can say that might be the doorway has to exist in this model and also exist in this model. And here, perhaps the stairwell has to exist in this model and also exist in this model, for example. So once you've got those two things going, then you can start to ask, how do we reason about once you have that idea, you can ask, how do we reason about these sorts of things? So interfaces, they have to mediate the compositional models. They have to build on the distributed system structure we just talked about. In practice, they have to involve the locations. There have to be locations which talk about where these things sit. You have to take account of what resources you expect to be there, and what actions are meant to be happening at the boundaries. And this kind of sounds obvious, but believe me, it's not quite true. Okay, what's worth noting is that when you connect, when you put in what an interface has to support is that a piece of the environment is going to be supported, is going to be replaced by another model when you bolt things together, and there has to be consistency at the level of the animation of the actions, between what it looks like when it's just the environment throwing stuff and when it's actually a model throwing stuff out of its output. So that's true. So here's what an interface is going to look like. There has to be a shared location. The idea is that these two are essentially the same location. So what we do is we implement the distributed systems model with location graphs labeled with resources. We explicitly identify actions associated with the identified locations in the interfaces. And then each model comes with a specified set of interfaces. Models may have many interfaces because they have to talk to many different types of things out there in the world, in different places. And so that involves specifying input and output locations and all the associated actions that go with those things. And we need to have some detailed algebraic properties, and the stuff I'm describing to you now has commutativity, associativity, and stuff like that. So it's kind of basically kosher. So now, we end up implementing models in a very direct and simple way. You're going to have a graph with resource labeled vertices. We're going to have some identified actions, processes, and locations that are sitting in the interface, and we actually and those things are going to, some of those things are going to sit in the specified set of interfaces. And an interface is going to consist of disjoint input and output locations, which you might just write like that. These are located actions. So what's going on here then? To remind ourselves, here's a model. It's got two interfaces associated with it. This one has an input location, which is the doorway. This model also has an interface, and it has an input location, an output location, which is also the doorway. This one here has the stairwell, which is shared with this model, which is the input and output location for those two things. And the actions are the actions here are the agent goes through door action, which is located at the door. And this is the agent enters the stairwell action, which is located at the stairwell. I told you it was a very simple model. Okay, so in practice, the models you actually build are tens of thousands of lines of code in the modeling language. I'm not going to bore you with that. You don't care about code, right? So the key thing I want to talk, I've done quite quickly, so that's good. I want to talk about is really now the frame property. So what we want to do is support compositional reasoning. A model M is composed of the model M1, it's composed of the model M2 via an interface I1 from M1 and an interface I2 from M2. And then what we want is a kind of frame rule. So think about concurrent separation logic here. This stuff started life at about the same time as concurrent separation. So here's the idea: here's a property phi which holds a model M before an evolution A occurs, and you become model M primed, a property phi holds, psi holds. And now what we want to be able to do is to support local reasoning about the properties of these models. Sorry, my thumb doesn't fit very well on this. So what we want to know is that we can bolt together another model N and another model N here, which has property chi, and preserve the property phi and psi that we started out with. So of course the real way to read this rule is as a rule from conclusion to premises, and computationally you want to start deploying abduction as a way of inferring necessary components in the premises so that the conclusion is supported. Now, the key thing here is this little side condition here, and that restricts the evolutions that you're allowed to think about here, that the ones which support the frame rule, to those are, the way we use it is to those evolutions are not, those actions that are not part of the interface. Right, so that's important, right?
It's not in the vocabulary or sort, as it were, not just the immediate transitions.
You could set it up either way, depending on how much coding you're going to do, but yeah. I mean, the main point is this, right? I mean, it's this. What you want to do is say, okay, any evolution that occurs in the blue bit outside of the yellow box has a property that is fixed. Any bit that occurs in the green bit that outside the yellow box has a property that is fixed. Ditto for this.
You have a couple of minutes there.
Sorry about this. My finger is really not doing very well. So, I want to come back. Good, there we go. So, the point is, what this allows us to do is to restrict, when we bolt models together and we want to reason about whether or not their composition is well formed, whether or not we get the right properties of the combined model we want, we can restrict that reasoning to precisely those things that go on inside the interfaces. That's the only bit that's changed. So we can throw away all of the reasoning about the rest of the model, which is the big complex bit, and focus your attention on the bit that's going to cause trouble. And anybody who works with very large distributed systems will tell you that all of the trouble comes at the interfaces, right? And so what we want to do is restrict the attention precisely to those points. So, next steps here. Well, what we want to, there's a lot of refinement of the definition of interface. Your point there, Samson, is pertinent to that. Exactly what is the right way to organise the data structure around that. Yeah. What are the useful abstractions? There is some underpinning logical theory to be cleaned up. I mean, so I only gave you the very slightest sketch of the kind of logics that are possible here with this kind of resource semantics. Actually, it's a very rich theory. I can give you pointers to the theory we've developed in recent years of that, but there's a lot of it there to be had. In terms of implementation, taking abduction seriously, so it's I don't know if you know about, my friend Pete O'Hearn does a lot of work with Facebook these days, and they have this tool called Infer, which implements separation logic for finding bugs, doing static analysis. And their abduction is a very, very important part of that theory. And what that does is allow you to run the frame rule backwards and calculate appropriate conditions. Okay, so that's an important thing. We don't really know how to do that very, very efficiently in the process algebra world. So. And we need to do. It would be lovely to do some more large-scale applications, networking, databases of consistency, supply chains is another obvious one. Actually, people are also thinking about weak memory at the moment, which is completely the other end of the scale. And we need to deliver some tools. Okay, thank you.
Samson?
So, in terms of the sort of the actual modelling and the using this, where are the key places where composition is used? I mean, is it to build things up or to take them apart, or?
So it comes in two ways, right? When you're trying to work out how to build models in the first place, you're staring at a big complex system and you're working out where the natural points to put these interfaces are. So that's the first place.
It allows you to break things
how
up
do you
into
decompose
pieces,
it? What are the natural chunks where the frame rule is going to give you enough restriction to make the reasoning practical? That's one thing. And then, of course, once you've done that, reconstructing compositionally as opposed to decompositionally, the properties of the composite model is what. So both ways around is important.
So is it fair to say that what you're describing here is a sort of a temporal frame separation rule? I mean, or do you think of this temporal version of the frame rule you wrote? Do you think of it as the same as the spatial version, which one is more used to?
This is temporal, yeah, because it's about concurrent actions, and they are going on. I mean, they're just ticking along as they do, but yeah, it is focused on the action rather than on pointers or whatever. Yeah, sure.
Please.
Could you give a specific example where you use abduction?
Well, abduction. I mean, that's the next piece of work to do, right? So, but I mean, the place where that's really kicking ass at the moment is in the Facebook tool Infer. So Infer is an implementation of separation logic intended to do static analysis for bug finding.
I mean, in this context of a security
Well-
setting.
So let's see. I might assert that I want to have. So here I've got some guy coming into a lobby, and what happens here depends on the presence of a number of different types of resource. You know, the number of security guards, the number of reception people, the number of entryways, perhaps some properties of badges and stuff like that. I might want to put a efficiency constraint or a cost constraint on the traffic flow through this model. Right, so that would be a property in the conclusion of a frame rule. And in order to calculate, what I want to do is to calculate how many guards, how many entryways, how many receptionists I need in order to achieve a particular cost constraint. So I would run the rule backwards and do some calculations to find that.